Now that we've defined the exponential mechanism, let's try to get some mileage out of it. In particular, we'll see that it's very easy to apply it in different settings. All you have to do is set up the inputs to the problem the right way, define the score function carefully, and then we'll see that the sort of guarantees we want just pop right out of it. So in particular, the first thing we're going to see is our old friend, the Laplace mechanism. And actually, the exponential mechanism can actually express it fairly easily. So what is the setting? We're imagining that there's some sensitive data set x, and we're trying to compute f of x, where f is sensitivity delta. So let me just do it real quick. The data set is going to be equal to, we're going to define the data set as x. The objects, the set of objects that we're going to consider as possible outputs, is going to be the real line. Recall that this is like a real valued function, so we're going to consider as a candidate every single point in the real line. There's infinitely many here, but we'll see that this isn't really that big a deal for this case. And the last thing here is the score function. So the score function is just going to be defined as the following. This is going to be a little bit arcane looking, but we're going to define it as negative of the absolute value of the function at that point, on the data set minus the value of h. So it's a bit weird, but let's see what this defines as a distribution. Well, now we have that the probability that the exponential mechanism on some x equals some particular h. Remember, we said that this is going to be proportional to x of minus epsilon times the score function at this point. So yeah, in particular, just subbing that in. You notice I already put the minus in front there. Minus h divided by 2 delta. And this is exactly the density of the Laplace mechanism. You just compare the PDF of the Laplace distribution, and this is exactly it if you sub in the appropriate parameter needed in order to guarantee privacy. So actually, there's one thing that's a bit different here, which you might have been staring you in the face. And the difference is the fact that we have this factor of 2 here. In some sense, this corresponds to adding twice as much noise as we would need for the Laplace mechanism. In particular, the Laplace mechanism would have probabilities proportional to this. But here, for whatever reason, we're still guaranteeing epsilon differential privacy, but we have this factor of 2 here. It turns out, well, I mean, if you've analyzed the Laplace mechanism directly, you'll see that this factor of 2 can be removed. But why does it pop up here, and why can we remove it? Well, the reason is the following. The reason it appears is if you take a look at the privacy proof, recall that there were kind of 2 components in the privacy proof. One where we sort of dealt with, we paid epsilon over 2 for the numerator and epsilon over 2 for the denominator. So the epsilon over 2 for the numerator still stays there, but the epsilon over 2 for the denominator doesn't actually apply here. The reason is because in general, you can actually have the normalization change when you change the data set on one point. But in this case, when we're looking at a Laplace distribution, in fact, this specific class of functions won't have to pay this just because it's well behaved, and the normalization will always be the same thing. So in fact, in this case, we can do better and save this factor of 2. But the main point here is just to show you the fact that this is in fact an instantiation of the exponential mechanism. Cool. So that's a nice and easy application. Let's see another application, which is closer to the one which we had at the beginning of the previous part. So this is selling one digital good. Recall that there's as the following setting. The seller has like infinite copies of one item, and they need to choose price P, which is going to be, we're now going to normalize everything to be within 0 to 1, just to keep it nice and bounded. And there's going to be n buyers. each of these buyers will have some valuation VI, which is in 0, 1. And like we said, if their value is greater than or equal to the price, then they'll buy it. If not, they don't. As a result, we have the revenue of the seller at some given price P is going to be equal to the price P times the number of people whose value is greater than P. So that's the revenue. And if this was in a non-private setting, what the seller would do is they would just simply look at all the valuations and pick the price P, which would maximize their revenue right here. That's their goal, trying to maximize the revenue, of course. But this is, of course, first of all, not private, which we sort of commented on before, something we want to be private with respect to their values. But additionally, there's other neat combinations or connections between game theory and differential privacy. I'll just talk very briefly about this, but mention that it has implications for truthfulness. By truthfulness, I mean, we want that the buyers will be incentivized to tell their true value. Well, in fact, if you tell them that their bids are going to be put into a differentially private algorithm, then in fact it will be then you're telling them essentially that their bid or their value will have very little impact on the final price. It doesn't have much chance of changing it anyway. Therefore, they have no incentive to lie, or minimal incentive to lie. Thus, in somehow there's like connections between truthfulness or strategy proofness, as it's sometimes called, and differential privacy. But I'll refer you to section 10.1 of Dwork-Roth if you want to learn more about this connection. But yeah, for now we're just going to focus on the differential privacy motivation. We're just going to imagine we want to do this for the sake of privacy. Okay, so this is the revenue, and let me just actually write as shorthand gamma to be the maximum possible revenue that they could incur. So the max over P of P times size of I VI greater than or equal to P. And yeah, that's sort of the best revenue that they can possibly have. But that's, of course, not private. So there's sort of two steps that we're going to do before we apply the exponential mechanism. Well, we're going to discretize the domain first. The reason is because before we had it very nice, somehow we got miraculously lucky and the PDF just nicely, lined up and gave us this, the nice distribution, which we know how to sample from. But if in general, these VIs are placed at very weird locations, then this could give us a rather unusual distribution, which we don't know how to sample from. So what we're going to do is discretize the domain. So, if you were just doing this, without any further change and you didn't care about sampling things, then what you would do is set H be equal to the interval 0, 1. But like I said, we can't do that because it's not clear how we're going to be able to sample from the resulting distribution. So instead, what we're going to do is we're going to set H to be equal to the following discretization of this interval. So we'll consider the set of points alpha, 2 alpha, all the way up to 1, where alpha is going to be some parameter which we're going to set later. Importantly, we will go from this size of the H being infinite to now we're going to set have H to be the size of H rather to be 1 over alpha. So that's important. That's sort of relatively small, let's say. It depends on what alpha is, but it's going to be relatively small. So how much is lost? Like before we knew that gamma was the most that we could get from the gamma was the max revenue we could possibly achieve as the seller. So let's now see what the max revenue we can get here is under this discretization. And I claim that the opt for on a set of values is going to be greater than or equal to gamma minus alpha times n. And let's think about why this is. So suppose we perform the discretization, and that is we're restricted as a seller to only choose a price from the set of prices. Well, suppose you knew what the optimal thing before was, say some P star, then you're going to reduce it from P star to some P prime, where the difference between P star and P prime is going to be less than alpha. Basically, you round down the optimal price, whatever price achieves this gamma, to the previous multiple of alpha. And the idea is this will change the price by at most alpha, and that as a result will be alpha lost from each individual who is actually buying it at the previous price. So since there's at most n individuals who are buying it at the previous price, therefore the new optimal revenue after this discretization is going to be decreased from the previous one by at most alpha times n. So that's sort of how much we pay for now by the discretization, but there's still the cost that we're going to pay via the exponential mechanism. So let's instantiate the exponential mechanism. It's fairly easy. So what are we going to need? We're going to need, the data set will be, the vector of v's, the vi's. We have that, h will be this. We have already defined h. And then finally, the last thing we're going to need to do is we're going to need to define the score function. And the score function is just going to be the revenue. So let me write it a bit more in the familiar form that we've written. So the score in the data set is the values, and the objects are the prices, p's. And so what we're going to do is let this be equal to the revenue. P times the number of individuals who have value greater than or equal to P. Okay, so we have the score function, and the final thing we need to do before we can run the exponential mechanism is look at what the sensitivity is. Well, it's not too hard to see that the sensitivity is upper bounded by 1. Why is that? Well, let's note that this term, by changing one individual in the data set, like one price, you'll see that the size of this set can only change by 1 at worst. And we also know that P is within 0 and 1. P is chosen to be bounded within that. So the upper bound on delta is going to be 1. That's everything we need to define the exponential mechanism, and you can run it. You can just sample things with probability as defined by the exponential mechanism. It's private, as we know, so let's look at what the utility is going to be. So the utility is going to be, using the guarantees of the exponential mechanism. Like, I'm not going to write it out again, but I'm going to say roughly, you can work this out more formally and with like the tail bound and everything, but it's going to be roughly this quantity here, 2 delta over epsilon times log of the size of h. And what can we say about this quantity? Well, this is greater than or equal to, first we have one bound on the opt. So this is gamma minus alpha times n. And then this term here, let's just substitute everything in. Well, this just becomes minus 2 over alpha epsilon. Sorry, not 2 over alpha epsilon. 2 over epsilon times log 1 over alpha, where this log 1 over alpha is just log of the size of h. So now we see how much we've lost by running the exponential mechanism and this discretization together. Gamma minus alpha n minus 2 over epsilon log 1 over alpha. But how do we combine these two? We want to combine these two into, there's sort of a trade-off here with how we set alpha. Recall that we still have to choose it. So if you set alpha to be something like log n over n times epsilon, then this will give you that this is greater than or equal to gamma minus O of log n over epsilon. Just substitute it in if you want to check yourself. But this is really cool because what this shows that we can we can use the exponential mechanism to get a result privately, which is only an additive log n over epsilon off from the true thing. Like, why is this pretty good? I mean, imagine n is very large, and you could get most of the people to pay a constant amount for it. Say like n over 3 people would pay 0.1 for it. Well, then you can get something which is omega of n here, and this is a very much a lower order term here because it's just going to be logarithmic in n. So this gets you a very nice accuracy guarantee for this problem. Cool, so that's the formalization of the selling one digital good that we talked about earlier. We'll move on to the final application. Oh, what's this doing here? We'll move on to the final application, which is private Pac Learning. So Pac Learning is kind of the granddaddy of machine learning nowadays. This sort of model was formally defined by Les Valiant Turing Award winner in 1984. We're going to define it or describe it non-privately first. And for now, we're going to focus on Boolean functions over the Boolean hypercube. Yeah, what does that mean? It means a Boolean function means that the output is either going to be 0 or 1 of the function class, and the Boolean hypercube means that the domain of the data set is going to be 0, 1 to the d. So this might be a little bit arcane for now, what I'm talking about, but let's see. I'll sort of be a bit formal first to define it, and then we'll see an example. So an algorithm will be given the following objects. It'll first be given a concept class. So this is going to be a set of functions. So C is going to be a set of functions which go from 0, 1 to the d. This is what I was talking about, the hypercube. And it's a Boolean function because it's going to map from the hypercube to 0, 1. So this is our concept class, and the idea is that we're going to be looking at a set of functions which map points to some labels. So you can think of this as your set of possible classifiers, which could be the ones which correctly classify things. So that's the concept class, and it's also given a set of n elements. So there's like the data set. We're going to be it's going to be given xi comma yi, where these are the like data points and these are the labels, and the labels are going to be according to some function c, let's say c star of xi. So what I'm trying to say here is that there exists some c star in the function class, concept class C, from which the labels are being defined. And furthermore, the data set is drawn IID from some distribution D, which is these are unknown. This is unknown to the learner, as is the distribution D. It's just given some data set and some class of functions, which might be rather large. But from this, it has to figure out, the goal is, given this, to output some function which would do well on a new example. The goal is the following. It's to output some c hat such that we have the following type of guarantee. Say that probability that this function c hat, when applied to a new sample drawn from the distribution, this is unlikely to disagree. This is unlikely to disagree with the true function. And then this is we want this to be small. And we'll quantify precisely how small. So, okay, that's the Pac Learning setup. This is perhaps a little bit abstract, so let me try to do an example. So, one of the most canonical examples for this type of thing is learning of half spaces, let's say. So let's suppose that there's some unknown half space. So this is going to be well, by a half space, I mean, everything that's on this side of this line is going to be a 1, and anything on this side of the line is going to be a 0. So this thing here is going to be, the C star, which is unknown to the learning algorithm. And the idea is that there's going to be some data points which are drawn according to some also unknown distribution, which are going to, be labeled. So for example, the blue points are going to be those which are 1s, and I'll draw, say, other colored points which are going to be 0s. So yeah, you can see here that we drew a bunch of points which were from some distribution D, and we can see that they're labeled somehow. Imagine you didn't have this orange line here telling you where they are. Well, you can see kind of, okay, there must be some line between these such that things on one side of the line are +1 and things on the other side are going to be 0. So imagine you saw only the set of training data, that is the blue points and the green points, and then maybe you could guess, okay, maybe my half space is going to be something like this. So that would be your C hat, because it's your sort of guess based on seeing only the training data. And in fact, you can probably argue, if you have enough data points, that this is going to be pretty similar to the true function in terms of how it classifies things. There's only some things which it would disagree with on. For example, like basically anything between these two lines here, and similarly these two lines here. These are the ones sort of that it gets. These are sort of the witnesses to this inequality, or to this probability statement here. So yeah, hopefully that elucidates what I mean by the Pac Learning model. And this is very classically studied, has enjoyed a lot of study, and we have a very good understanding of it. In particular, let me tell you about one of the basic examples or basic theorems in the setting in, say, non-private learning theory. So let's suppose, basically it says that if you take n to be at least the log of the size of this class C, then we're going to get something which is pretty good. So let me write this lemma. If n is greater than or equal to, let's just say much greater than log of the size of C, then, or alpha squared, let's say, then there's an algorithm which can output a C hat with the following guarantees. X sample from D. Sorry, I forgot this X here. Basically, the probability that it errs on a new sample would be less than alpha. So, okay, let's see how we do this. What is the algorithm, first of all? The algorithm is the following. You simply, generate your training data. You get your training data. What you do is you consider every single function in the class C, and you see how if it ever makes a mistake on the data set X. And anything that doesn't make a mistake ever, then you output it. And the claim is that anything that never makes a mistake, no errors on the training data set. This implies that there's like less than or equal to alpha error overall. In fact, for now, for mysterious reasons, let's say, let's set this to be alpha over 2. It's not a big deal. You can just change a factor of 2 there. So yeah, the claim is that no errors on train will result in less than or equal to alpha over 2 errors on the sort of on the population, as we call it sometimes. Meaning, if you drew a new sample from the distribution, then the probability would error. Okay, so let's see how we prove this. And this is a kind of classic style of argument, which is kind of, we call it Chernoff, I call it at least a Chernoff bound and union bound style argument. And the way we're going to do it is as follows. So we're going to look at the following quantity. This is just going to be the number of, let me write it first. Okay, sorry, let me say first, we're going to fix one specific H. So we're going to just, maybe it's not the perfect H, but we're going to fix some H in the concept class for now and see how well it does on the training data, and then sort of see if we can infer anything about how well it does on the overall population. So what we have here is, the fraction of errors it made on the training data. Sorry, the fraction that it got correct, rather, on the training data. And we see how that compares with the sort of population error. So that is probability X sampled from the distribution, that H on Xi is equal to C of Xi. And I guess in all places this should be star, because this is like how often it matches with the true function. So the neat thing is that, you know, these are sort of the same. The expectation of this random variable is going to be equal to this. This is not too hard to see because it's just a sum of random variables, each with expectation equal to this, and then you sort of normalize it. So yeah, this is the expectation of this random variable is equal to this quantity over here on the right. Now this is nice because we know very well how to control how far things deviate from their expectation. So all we're going to do is, you know, use a Chernoff bound here. So all we're going to do is say that the probability that this is greater than or equal to say like alpha over 2 is going to be bound by the following. So this is what is this probability even over? Like what is the sampling process here? Well, this is over the, recall that this is sort of a quantity on the training data, and this is going to be sort of a population level quantity. This is just a fixed number. But really what we care about is this random variable here. So the sampling process is where these are drawn from x1 through xn from the distribution D. So, okay, we're trying to say what is the probability that it deviates from its expectation by more than alpha over 2? Well, if you think about it, this is just going to be a sum of 0, 1 random variables. And that makes it ideal for applying the Chernoff bound, which we've studied already. So take a look at the notes and look at you know, how to apply the Chernoff bound here, but you'll just see that this essentially lets you bound this with, it's also using the value of n here. This will become, you know, what do I want to say? This will be upper bounded by exp of minus log of size of c, which we can, if you just sort of let the exp and the log cancel out, and you put a big enough constant in front of this, which is hidden here, then this is say like less than or equal to 1 over size of c to the say like 10 or something. Yeah, the point is just putting a big enough constant here will cause this probability to decay very fast. So okay, what did we do here? We did a Chernoff bound argument saying that for any specific hypothesis in the concept class, it'll have very close, you know, matching between its empirical training loss versus the number of training errors it made versus the number of errors, the probability it would err on the population. But now we know that's very, very low, so that differs. So we can just take a union bound, and then you can say for all h simultaneously, we have this guarantee above. And that's with probability, you know, sorry, we have that this probability that this is small. Yeah, it's not this guarantee exactly, but it's the probability that, I'll just write it in words, that empirical number of mistakes, like the empirical fraction of mistakes rather, is approximately equal to the like population fraction of mistakes, plus or minus say some alpha over 2. That's all this is saying, that the empirical fraction and the population fraction are the same up to an additive thing. And this happens with all simultaneously with probability greater than or equal to 1 minus, say, like 1 over c to the 9. That's a union bound type argument. Okay, so that shows that, what have we done now? We've shown that for all of them at the same time, that the kind of empirical fraction of mistakes is equal to the population fraction of mistakes up to an additive alpha over 2. So now the proof is easy to finish, because consider any function in the class which made 0 empirical errors, so 0 fraction mistakes here. We know there's at least one of these because the true function c star would get 0 error. This implies that the even if we get that one wrong and we output anything else which has a 0 empirical error, well, this inequality tells us that basically this relationship here, in fact, tells us that the true population fraction of errors it would make is alpha over 2. That's an upper bound on it. And that completes the proof. Just output anything that never made a mistake. This is sometimes known as the Occam's razor rule in machine learning. So, okay, we studied the non-private problem. You can see it's very simple to analyze and say what the complexity is. And importantly, you can see that the sample complexity we need, the number of data points we need in order to get like a small error, is roughly logarithmic in the concept class. We can actually do somewhat better than that, but using something known as the uniform convergence theorem. But yeah, for simplicity, let's say log of the size of the concept class. Now, what if we want to do this under differential privacy? Well, under differential privacy, let's see first of all what it even means to do it under differential privacy. Well, what is a neighboring database? A neighboring database is when we change a single point xi, yi to some other point xi prime, yi prime. And this is going to be like, this is a sort of an adversarial change. What do I mean by that? Well, remember before we had, in the when we were trying to go for the accuracy analysis, we had it such that that the x's were defined according to some distribution. So xi was drawn according to d. But here, now, like xi prime is not necessarily this looks weird, but it's not necessarily distributed according to d. It's an arbitrary adversarial point. That's one thing. And the other important thing is the fact that, additionally, this yi prime, it does not necessarily have to be the correct label for what the function would predict on xi prime. It can be arbitrary. It can be either 0 or 1. And this shows us that like the idea is we really want to allow arbitrary changes to the data set for the sake of privacy. This is sort of a more philosophical point, in fact. Yeah, we kind of want accuracy when the data is actually drawn according to a distribution. That's where we'll usually prove our accuracy guarantees. But we want privacy worst case no matter what change is made to the data set. This is because if we have some model misspecification, like we make a mistake on our side in terms of guessing what the distribution should be like, we don't want the user to have to lose out on their privacy as a result. Okay, so that's what it means for it to be differentially private in the sense, this is the neighboring data set concept, and then everything else just follows the same way. We just want the probability that we output any particular function to be, bounded, and the ratio of that under two neighboring data sets to be bounded. Okay, so we're going to use, surprise, the exponential mechanism. How do we specify this? Well, the data set is going to be the, x comma y is the data set, all the points and their labels. We're going to let the set H be equal to the concept class C. That's natural because we're going to try to output one function from the concept class. And the last thing, which is not the most sort of mysterious one, to maybe the one that needs the most inspiration, is how do we measure the score for a single thing? And we'll let it be minus size of the following set. Yeah, this quantity here. So this essentially says that what we do is we count, we're going to want it to be normalized as well. We look at the fraction of points which it gets incorrect, and we negate it. Why do we negate it? Because think about the best possible one, which gets everything right. Then this value would be 0. So we wanted to, exponential mechanism picks out the thing with the maximum score. So really the ideal thing should be 0. I mean, alternatively, we could look at positive of the number of mistakes it does make. The number of things it gets right, but for now, we'll just do this. So, okay, and importantly, what is the sensitivity of this? The sensitivity is equal to 1 over n. And just by seeing that, changing one data point, it can change that size of that set by at most 1. Okay, so now these things here, these like definitions and the computation sensitivity are all we really need. Why is that? Well, let's see what the quality of the an item that's given by the exponential mechanism, the sort of C hat, what's its score? Well, what the exponential mechanism says is that it's going to be greater than or equal to 2 times delta over epsilon log of the size of h. And what is this equal to? This is equal to 2 over epsilon n log of size of c. Now, this is sort of the, what are we going to do? Like, what are we going to take n to be? Remember, before we had n is greater than or equal to alpha, 1 over alpha, log c over alpha squared. Well, now I'm going to take the value that n is greater than or equal to, well, let's just say just like n is much, much greater than log size of c over alpha times epsilon. If we use this condition, oh, sorry, let me mention that there's minus signs here, importantly, yeah, because, yeah, there's a minus sign there. Okay, so if we take this to be much greater than this, then that tells us that the score of whatever we get is going to be greater than or equal to alpha over 2. So what does that mean? That means, like, the score function is this, so that implies that the empirical fraction of things that gets wrong, h on xi does not equal yi over n. This implies that it's less than or equal to alpha over 2. And what we're going to do is combine this tells us it's going to output something with like a small number of empirical errors. What we do is we combine that with the following sort of concentration bound that we used here. We noted that the empirical number of fraction of mistakes is going to be approximately the population fraction of mistakes up to an additive alpha over 2. So basically, you know, this statement here combined with this statement here, this sort of like the cost due to privacy, this is the cost due to just sort of random sampling. But if you put those two together, it gives us the following theorem. If you take n to be sufficiently large, that is n is greater than log of size of c over alpha squared plus log of size of c over alpha epsilon, then we have a probability of making a mistake on a new sample is going to be bounded by alpha. And, you know, half of that comes from each of these two sources, overall giving a bound of alpha. So let's take a step back and reflect here. What did we really do here? We started by looking at a non-private algorithm for doing Pac Learning, and we saw that we could do we only needed a logarithmic number of samples, where log in the number of in the size of the class. And this shows us that if we want to do it both privately and get both privacy and accuracy, then we only need still logarithmic in the size of the concept class C. So let me just mention now. The point is that, you know, if you consider this C to be the large part, the thing we're paying a lot for, then we didn't really pay you know, much more in order to get privacy as well, which is a very convenient thing. Some would say we got privacy for free in some sense. So all we did was a few examples to really show you that the exponential mechanism is very powerful and very easy to use. Once you like define the sort of score function and the set of objects correctly and then compute the sensitivity, it's very simple to apply, and it'll give you some good algorithms, you know, with fairly little work. It's a good starting point in the sense that it'll get you a good accuracy. It might not always be computationally efficient in some cases because of the fact that it has to essentially iterate over the entire set of objects H, but you know, it'll get you something, and then you can go from there in terms of trying to get something that's computationally efficient. So yeah, the exponential mechanism is a very useful tool and one you should really master in your adventures through differential privacy.